Okay, let's start. So, I'm Deblina Maity. Okay, wait. Okay, Sukriti, can you hear me?
Yeah.
Okay, thank you. So, let's start. So, I'm Deblina Maity. I'm a research scholar in the Department of Mathematics, IIT Kharagpur, and I'm also in PMRF-NPTEL TA for the course Basic Real Analysis, and the course instructor is Professor I.K. Rana. So in this session, we are going to discuss some problems from real number system and sequences. Right? I think you all have watched the video lectures from week 1, right? So let's solve some problems. First, recall some basic definitions. So you can see the notes, right? So the real number system is what? This is the real line, right? So the first, okay. So let's wait for 2 minutes. Okay, so this is the real line R, and first came the natural numbers, that is 1 2 3 like that. So the natural number is denoted by this n, and then came what? The rational numbers, which we denote by this q, and there are irrational numbers which will which is nothing but this r minus q, because the numbers which are not rational is irrational number. Now this natural number has this property. What property? The order property. This means what? This means if we are given two numbers from this natural number, we can say that it is a is less than b or a is greater than b. So there is a order. And in q, it also has this property, order property. Means what? If we are given two numbers from this rational number, then you can say either a equals to b, a less than b, or a greater than b. Right? So there is a ordering in the rational number system. Now it also has some property other than this order property, which is the field property. That is the algebraic properties. So there are 9 properties actually. Okay, I am going to write this. So this field property is, the first one is what? This is the commutative property. This means if you are given two numbers from q, then a plus b equals to b plus a. So q is commutative. And the second one is, it is associative. I am just quickly writing this because this is the basic. And third one is that field means there is two operation, plus and dot. So with this there are 9 operations. For first 4 considering this plus, and second 4 considering this multiplication dot, and the last property which connects these two. And the third one is what? This is there is a unique 0 in Q such that a plus 0 equals to a for any a. And third one is that fourth one, it has an additive inverse, that is for any a belongs to Q, there exists a minus a belongs to Q such that a plus minus a is the 0 vector. So these are the 4 properties of plus. And then the second multiplication property. For multiplication there are 4 properties. If AB is there, AB is also there, and ABC belongs to Q, then A of BC equals to ABC. And also there are multiplicative identity 1 belongs to Q, which have, so this means 1 dot A equals to A, and if A not equals to 0, then there exists an A inverse belongs to Q such that A dot A inverse is the multiplicative identity. Okay, I think there is one more property, that is AB is BC, BA. And the last property which connects these two, which is A dot B plus C equals to A dot B plus A dot C. This connects this multiplication and the addition. So this is the field property. And Q has this property. And this N does not has this property, because see, if any 2 are there, if 2 is there, 2 belongs to N, but minus 2 does not belongs to N. So like that, N does not satisfy all this property. So Q is ordered field, and R is also a ordered field. If you see in the videos, you can, so R is also a ordered field. So how to differentiate R? Q is also ordered field and R is also an ordered field, because R also satisfies this ordered property and field property, algebraic property. So to differentiate this, they came up with this property which is called the completeness property. What does it say? So it says every non-empty subset of R that has an upper bound also has a supremum. So this is the completeness property, and Q lacks this property. So that's why R is, and R has this property, so R is a complete ordered field. Right? Why Q lacks this property? If you take this subset, say S is what? All those rational numbers such that x square less than 2. So this set, for this set, root 2 is an upper bound, right? And the supremum is what? Supremum is nothing but the lowest upper bound. So the lowest upper bound is root 2, which does not belongs to Q. Oh sorry, this also has a supremum in R. It means the supremum also belongs to the set R. Here this supremum, which is root 2, does not belongs to Q. That's why Q is not complete. So Q is not complete, right? So you understand this? Okay. So now let's talk about the countability of these sets. So a set S is called countable when there is a injection, that is a 1-1 mapping from S to this natural number set N. Also this is equivalent to there is a surjection or a onto mapping from N to S, right? So this, if it satisfies this, then we say that S is countable. So you all know what is a injective mapping and surjective mapping? Can you please say?
Yes, ma'am.
Okay. So N is countable, right? Because N is the identity mapping from N to N. So N is countable. Then what about Q? Q is also countable, which we'll prove now. Now first, what about N union N? Is this countable or not? So first question is if N union N is countable. So how does it look like? So it is like Mn, where M and N belongs to this N. So this is countable if you have seen any book, or you can prove that actually. So countable means what? You have to find a mapping from N to this N cross N, N union N. So how will you do that? So you can find this is nothing, N, we can divide N by this odd numbers and even numbers, and we'll assign 1 to what?
Ma'am, is it N cross N or N union N? Ma'am?
N union N.
Okay, ma'am.
Okay. You can also prove this by, okay, it is N union N, right? Okay, I have written it wrong. This is not Mn, this is for N cross N. But we also know that countable union of countable sets are also countable, right? So if you take any union of this N union, say Q union, like infinity many times, or suppose any finite or countably infinite, then it is going to be countable set. So let's prove that. So what we will prove? We will prove that countable union of countable sets is countable, right? So first take some countable sets, which is suppose A1, A1 is countable, A2 is countable, and like this. And since A1 is countable, we can enumerate the objects like x11, x12, like this, since it is countable. And A2 is also countable, so we can enumerate like this. And An is what? Xn1, Xn2, like this. So we are going to find union of ai's where I is 1 to infinity. So we prove that this is countable. So how? So first, okay. So we have to find a mapping from F from union of this ai to this n, right? So this we have to prove this, since this is infinite set union of ai. So this F is going to be a bijective mapping, 1 1 and on 2. So how to define this mapping? So we'll define this mapping by what? So first we have to take two cases. So case 1 is what? All the AIs are mutually disjoint. Mutually disjoint means what? If we take any I and j which is not equal, then AI intersection AJ equals to phi. They are disjoint. If you take any ij which are different, then AI intersection AJ is disjoint, right? So in the first case, we will take this mapping F of this x mn. So this is a general number belongs to this union xmn. We'll take this to be 2 to the power m and 3 to the power n, okay, into. So this mapping is going to be bijective mapping. So you can clearly check this. If m is not equals to mn, not equals to m dash n dash, then if and x of mn, injective means what? If f of xmn equals to f of x m dash n dash, then m dash equals to m and n dash equals to n. This is what? This means this is injective. So this means what? 2 to the power m, 3 to the power n equals to, since they are primes, so 2 to the power m minus m dash equals to 3 to the power n dash minus n. So this means what? This means a number, this is a number, suppose x. So x is even 2 to the power something and x is also odd. So this means what? X has to be, so the power has to be 0. So this means m minus m dash equals to n dash minus m has to be 0. So this is actually 1. So this means m equals to m dash and n equals to n dash. So this means this is f is injective, and they are and this is clear, this is surjective, because if you take any number from this n, then you can find a number mn which is for which this f of xmn equals to this number. Since this is infinite, if injective means this is also surjective. So this implies what? We have found a mapping which is bijective, injective. This means union of AI is countable. In this case, where these AIs are mutually disjoint. So case 2 will be what? Case 2 is when they are not mutually disjoint. So this means all AIs are not mutually disjoint. Then what to do here? So first we'll make them mutually disjoint. How? So these are the AIs. So first let's take B1 to be A1, and the set B2 is A1 is given here, this set, and then we will take B2 to be A2 minus A1, and then B3 is what? B3 is A3 minus A1 union A2, and like this Bn will be what? An minus A1 to An minus 1, like this. It will go like this. So this is what this means. Each of these BIs becomes mutually disjoint, because say this is A1, but this B3 does not have A1. So all of this become mutually disjoint. So if I not equals to j, then BI intersection BJ is going to be phi. And also we see that union of these BIs is nothing but union of these AIs, because all of them are there. So if we prove that all these BIs are union of BI is countable, then union of this AI is also countable, right? And since this BI is mutually disjoint, and from case 1 we have proved that this union of BI is going to be countable, so this will imply union of BI is countable, and so this will imply union of AI is also countable, right? So countable union of countable sets is going to be countable. So all these examples like n union n, n union n, like this for infinitely many times, countably infinite, they are going to be countable. And q is also countable. We'll prove that. So now let's take about q. So why q is countable? Sukriti, you want to say something?
Yes, ma'am. I want to ask that how did we prove surjection in this case?
Surjection.
In the case 1, yes, ma'am.
It need not be surjective, but since because the theorem says if there is an injection, then it is going to be countable.
Okay, so we don't need to prove it.
No, we don't need to prove surjection, but
Yeah.
if the cardinality is same, but then there is going to be a surjection.
Mm-hmm. In
But
this case, there is no surjection. We are just saying injection.
is there any natural number which cannot be written as this? Okay, there are numbers which cannot, prime factors may not be this type of, like 5. You cannot write 5 to be 2 to the power something and 3 to the power something. So there may not be a surjection. But injection is there, right?
Yes, ma'am.
Okay, yes, you are right. So let's prove now this Q is countable. So we'll use this theorem or this property. This countable union of countable set is countable. How? So Q is what? Q, we can write Q to be union of these sets AIs where each A1 is like that. A1 is what? 1 by 1, 2 by 1, like this. A2 is 1 by 2. And like this goes on. So Q is union of these sets because these are all the rationals P by Q form where Q is not equals to 0, and union 0 also. 0 is also there. So because n, when n goes to infinite, this n goes to 0. So 0 is there. We don't need to take 0 from other way. So these are the unions and this is going to be Q. And each A1, see this each A1 is what? This is, there is a bijection from n to this A1 or an, because an is what? From n to n, this is 1, n goes to, will 1 goes to 1 by n, 2 goes to 2 by n, like this. So m goes to m by n, this means. So m goes to m by n. So this is the mapping. So all these AIs are countable and Q is union of these AIs, so Q is also countable, right? This means what? This means Q is countable. Now what about n cross n? It is also going to be countable because n cross n is what? Which I have written. So this is n mn, where mn belongs to this n. So we can also write this as 1 1 1 2 like this, and A2 is 2 1 2 2 like this. So n cross n is also going to be countable. And if you multiply it by finitely many times, it is also going to be countable. But for infinitely many multiplication, it may not be countable. We will see it later. Okay, so let's talk about sequences now. Now I have not talked about R. So we have seen that this n is countable, Q is countable. Then what about R? R is, and what about the irrational numbers? Are they countable or not? So you will see that R is not countable. I'll give a brief proof. So we will prove that 0 1 is not countable. Now 0 1 is a subset of R. So if this is uncountable, a subset is uncountable, so R is going to be uncountable. And how we prove that 0 1 is uncountable? We'll prove this by contradiction. So we'll suppose 0 1 is countable. I think you have seen the proof. So we'll prove this by contradiction, and this is a famous proof by Cantor. So since this is countable, we can enumerate this, right? So so the first number is, suppose this 0, like this. We are taking the decimal representation of this x1. and then x2 is like this, and xn is what? Like this. So this, all this xi's, this is the 0 1 we are saying, because this is countable, so we have enumerate. So these are all the 0 1s. Now we'll form a number in 0 1 which will not belongs to this set, all this xi, and we'll take this as the, we'll say that this is a diagonal approach. So we'll form this x. How? We'll take the first one, so the first term will be which is not y11. So this is x1 which is not y11, and then x2 is not y22, and like this xn which is not ynn. So we are taking a number which is not like the diagonal entries. If you take the diagonal entries, they are different. So this number, this x, differs from all the numbers, all the xi's, it differs at the diagonal entries. So this x does not belongs to this xi's. This means there is no xi's which coincide with this x, because it will not match at some point, at some diagonal it will be different. So this does not belongs to this xi's where I belongs to n. This means what? We have found a number which belongs, since this is a decimal representation, so this belongs to 0 1, and we are saying this does not belongs to this xi. There is no xi which is x. So this means what? This does not belongs to 0 1, because 0 1 is all these xi's. We have taken this to be countable. So there is a contradiction. So this means what? This means 0 1 is not countable. So R is uncountable. So R is uncountable. And we have proved that Q is countable. So this means what? All the irrational number which is R minus Q is going to be uncountable set. Is uncountable. Because R is what? R is union of R minus Q, union Q, and if both of them are countable, then countable union of countable set is also going to be countable. So R minus Q cannot be countable since R is uncountable. So the set of irrational numbers is also going to be uncountable, right? So now let's talk about the sequences. So sequence is what? A sequence is a mapping from n to the real number. This means we have the natural number 1, 2 like this, and we are assigning 1 to some x1, 2 to some x2 like this. So this is a mapping from n to r. And we say xn converges to L, some number in real number, if and only if the definition means it is an if and only if condition. This means for given any epsilon greater than 0, there exists a natural number n such that mod xn minus L is less than epsilon, right? This is the definition. Now if xn converges to L, then there are some properties. So first one is that xn has to be bounded. If it is convergent, then it is also bounded. So xn is bounded. Second is what? if it is convergent, then the limit should be unique. So limit is unique, right? And if we look at the subsequence of this sequence, then all the subsequence will also converge to L. Every subsequence of xn will also converge to L. Now we'll use these properties to solve some problems. Okay, so let's take the first problem. Use, okay, I will write this in. Use the definition of limit of a sequence to establish, first one is what? Limit of this so we have to prove this by the usual definition, that is the epsilon definition. So for the first one, so epsilon is given, right? So this is what this is, means xn is n square minus 1 by 2n square plus 3. So mod xn minus half, that is the limit half, is this is what? This is which is 5 by 2n square plus 3, right? So this is going to be less than 2n square, since and n square is also 2 by n. Now this is less than epsilon when n is greater than 5 by 2 epsilon. We can find some n which satisfies this property. So for that n, so there exists n such that for all n greater than n satisfying what? Satisfying n greater than this 5 by 2 epsilon, such that after this n, for all n greater than n, this xn minus half is going to be less than epsilon, right? So we have found an n. So this means limit is half by definition. Similarly for b is what? Limit of, so we'll write this. So xn is what? So this is what? We'll multiply denominator and numerator by n square plus n plus n. So this is going to be 1 and this is nothing but, so mod xn, mod xn is what? This is mod of, this all are positive, so this is less than 1 by n, and this is less than epsilon. For a given epsilon we can find some n for which 1 by n is less than epsilon. So there exists n such that n is greater than 1 by epsilon, and then for all n greater than this capital N, this mod xn minus 0 is less than epsilon. So this means limit of this xn is 0. So if you tell them to find the limit by the definition, then you have to check it by this epsilon property, right? Now let's take another example. What about limit of this sin n by n exist or not? Can anyone answer if this is a simple one? You can try it. Sukriti?
I think it should not exist.
Why?
If we break this down, that limit sin n by n and
Yes, one will be bound, one will not be convergent. That is the
Yes.
minus 1 to the power n by n. But
Yes,
what
ma'am.
about the sum? If both are not, see, this is what, this is xn is clearly if we break it down, the first one will not be convergent. But what about the sum? It may be convergent or may be divergent. So if we take the mod, see, it will be bounded by this what? So minus 1 to the power n is bounded by 1, and sin x is also bounded by 1, mod of sin x. So this is mod of by n, right? And this is what? This is bounded by 2 and this is n. So we can find this is for epsilon greater than 0. This happens. We can find an n for which this is less than epsilon. So this means what? This means xn minus 0 is less than epsilon for some n, for all n greater than some n, and n is what? N is greater than this 2 by epsilon, right? So this is convergent, and where does it converge? And this xn converges to 0, right? So this is a convergent sequence. Okay, oh God, I'm writing this in red. Okay, the another example is, what about limit n cos n factorial pi by 2, right? This is n cos n factorial pi by 2. What about this sequence? Can anyone guess? See, I have told you, if it is convergent, a sequence is convergent, it must satisfy all this property. It has to be bounded, the limit is unique, and every subsequence converges to the same limit, right? So now look at this sequence. N cos n factorial pi by 2. So first term is what? First term is n pi by 2, this means 0. Second term is, this is 2 cos pi, that is minus n. N3 is what? 3, that is n, and from up to after n, when n greater equals to 3, xn is going to be 3 n, because there is n factorial, so 2 will be cancelled and this is going to be n, right? Okay, so this means what? Xn is n means what? Xn is not bounded, it is going to be infinite when n goes to infinite. So this is not bounded means it is not convergent. This is simple. So xn is not bounded. This means xn is not convergent. Right? Okay. Okay, let's take another one. See, sine 1 by 1 plus 2 to the power n. So is it convergent? I'm writing this convergent or divergent. So can anyone guess? No? Okay. So if we take this sine 1,
I think it is convergent.
this is what? Convergent. Can you tell me again?
I think it is convergent, ma'am.
And convergent to what? Converges to
1.
1. If n goes to by clear eyes, if n goes to infinity, so this term, this 1 by 1 plus 2 to the power n is going to be 0. So this is going to converge. If it is convergent, then this is going to converge sine 0, which is 0. So if it is convergent, then it is going to be 0. Right? And yes, this is convergent. Why? Because this sine 1 by n is convergent. Why? Because sine x is less than x for small x, right? For some n greater than n. For small x, sine x is less than x. I think always maybe. So this means what? This means mod of sine s is less than mod n, and clearly this means what? This means limit of sine 1 by n is 0. Right? So sine 1 by n is convergent. And what is this? This sine 1 by 1 plus 2 to the power n. This is a subsequence of this sequence sine 1 by n. If we take n to be some 1 plus 2 to the power k, then this is going to be this x n is what? x1 plus 2 to the power k is sine 1 by 1 plus 2 to the power k. So this is a subsequence of xn, a subsequence of sine 1 by n. Okay, Arya, you want to say something?
Yeah, I just had a doubt. So any sign value will oscillate between -1 and 1, right? So
Yes, yes.
it can how can it not be divergent? Because then it will function like a harmonic series, right?
Yes, but here
I think
it is not sine x, it is sine 1 by n. When n going convergent means what? After some time, after some n, it is going to be close to some numbers. Right? We are taking all the positive this sine n, you are telling me this sine n is what? Sine n is oscillating. But when we are taking the values sine 1 by n. This 1 by n values are positive, right? They are belongs to this number, and when we are going to n going to be infinity, this is going to close to here. This is 1, this is half, this is some 1 by n, like this. So how does the sine x looks like? It is 0, and there is some pi by 2. So 0 to pi by 2 is 1. So this is like this, something like this, right? And we are taking the values in positive, 1 by n. So here it is continuous also, and when this is going to close to 1 by n is going to infinity, then 1 by n is going to 0. So it is going to be close to, very close to 0. That's why it is convergent. We are not taking sin x. X is not arbitrary. X is 1 by n. Do you understand now?
Yeah, got it.
Okay. So sin 1 by n is convergent, and this is going to be 0. So sin 1 by 1 plus 2 to the power n is 0. We will discuss the convergence about sin n, because sin n will be an interesting sequence, right? It will be positive and negative when n is increasing, because sin x, how does it look like? This is 0, 1, like this. So it is going to oscillate. So we'll discuss about this sin 1 by n. Okay, now let's discuss about this one. So problem number, say, 3. So discuss of this sequence sin n. Okay. So let S, we are denoting S by sin n. Right? Now clearly this is an oscillating set. So it is going to be divergent, but we have to prove that. Divergent means what? It is not convergent. So divergent means what? Xn, a sequence is divergent means if we are given any number c in real line and a natural number n, then what? Then there exists an epsilon greater than 0 for which there exists n greater than n such that this xn minus c is greater equals to epsilon. This is the negation of convergent. In convergent for given any epsilon greater than 0. So here it is, there exists, we have to find an epsilon greater than 0 for which it is not going to be close, and we can find this xn such that this c and xn are distant from this epsilon. So this is the definition of divergent, right? So you have to prove this S sin n is divergent. So first see that this sin pi by 6 is what? Half, and also sin 5 pi by 6 is also half. So this means what? This means sin x is greater than half when x belongs to between these two, pi by 6 and 5 pi by 6. When x lies between here, then sin x is greater than half. Also Similarly, since 7 pi by 6 is minus half, and this is same as 11 pi by 6. So sin x is less than minus half when x belongs to this range 7 pi by 6 and 11 pi by 6, right? So let's generalize these sets, this pi by 6 to 5 pi by 6. So for each k in n, denote ik by this set plus what, 2 pi into k minus 1 right? And when x belongs to this ik, then sin x is greater than half, right? Now see the length of this ik, which is what, this is 5 pi by 6 minus pi by 6. So this length is going to be greater than 2, at least 2. So the length of each ik is greater than 2. So this length is greater than 2 means what? So at least 2 natural number is between this interval, right? Since length is 2, greater equals to 2, at least 2 natural number is there. So this means at least there are 2 natural numbers in ik, and let's say mk be the first one. Let nk be the first one. So there is ik, this is ik, and nk be the first natural number which belongs to this ik, and we are taking the collection of this sin nk's and denoting it by s dash, right? So in this sin s dash, for all the values of this s dash will be greater than half, right? Because this belongs to ik. So this means all the values of s dash lies in half to 1, because sin x is bounded by 1. So this is going to be half to 1. Similarly, if we, if we consider jk by what, this 7 pi to right, this is jk's. So if x belongs to jk, then sin x is less than minus half. So similarly, this length is greater than 2, so there is a natural number, 2 natural numbers in this jk, and let's mk be the first one. In a similar manner, so, and we are denoting by this s dash by sin mk. So all the values of this s dash, So all the values of this S double dash lies in between -1 to -up, right? So now so this is the -1 to 1, right? This is the range of sign in. Now we are saying is the value of S dash lies between this half to 1. This is S dash lies in between this, and S double dash lies between -up to -1, right? Now this is the range of S dash and S double dash. Now we have to prove this is divergent, so we have to take any value C. So clearly if we take any numbers C from this -1 to which is outside this interval -1 to 1, like this C, so sin n is not going to converge there because there is no sin n values are there. So if it is convergent, then it must converge between -1 to 1. Now if we take any C in -1 to 1 and first take the epsilon, so we have to find epsilon, so we'll take epsilon to be half, and we'll see that if we take any C anywhere, then the half neighborhood of this will be outside S dash or S double dash. If we take C here, then C is outside S dash, and this if we take C anywhere between -half to half, then at least one of will be outside S dash or S double dash from the epsilon neighborhood of C. So I am saying is that S dash or S double dash, at least one of, not both, at least one of S dash S double dash will be outside the half neighborhood of C. C is any real number in -1 to 1. So do you understand this line? If we take any C and take the half neighborhood, any of the at least one of S dash and S double dash will be outside, right? And then this means what? If suppose S dash is outside, so suppose S dash is outside of half neighborhood of C. This means what? So this means we can, S dash is outside of this neighborhood, so C is here and S dash is, suppose this is the half neighborhood of C, and this is S dash, and S dash is what? S dash is all this sin nk. So we can find a natural number. So if we take for each n belongs to n, we can find a natural number nk which belongs to S dash. We can find nk belongs to this ik, and nk is greater than this n, such that this xnk, that is sin nk minus c, is greater or equals to half, right? So this is outside half neighborhood of C, means this. if we take any natural number, we can find nk from ik such that this sin nk minus c is going to be greater than half. So this means outside of the neighborhood of half. So this happens means it does not converge to c. And so this means xn, that is sin n, does not converge to c, and since c is arbitrary, so it does not converge. So this means sin n is divergent because c is arbitrary. Right? So all of you understand this? Okay.
Yes, ma'am.
Okay, let's take another problem. Problem number 3. Okay. Oh. So let xn be a sequence, right? And x2n, x3n, these are the subsequence, and x 2n plus 1 is convergent. Then prove that xn is also convergent. So the 3 subsequence is convergent, then you have to prove xn is convergent. See, if we are given that x2n and x2n plus 1 is convergent, then does it imply xn is convergent?
Yes, ma'am, it should.
Why?
Ma'am, because x2n means all the even subsequences and
But I
x2n
have
is-
not tell that this is going to the same limit. x2n and x2n may go to different limit, because if we take this sequence minus 1 to the power n, you will see that x2n will go to 1 and x2n plus n will go to minus 1, right? So both of them are convergent, but xn is not convergent. But if you are given that x2n and x2n plus 1 is convergent and they are going to the same limit, then xn is convergent. So okay, we'll prove this 4 later. I'll question, suppose xn is a sequence. Okay, this means xn is not convergent. So xn is a sequence, x2n and x2n plus 1 is convergent and they have the same limit. Same limit, which is L. Then xn is convergent. Okay, we can prove that this is easy. Since they are converging to the same limit, so x2n converges to L. This means what? There exists n1 such that, and given suppose epsilon is given, so n1 such that this x2n minus L is less than epsilon, right? also x2n plus 1 goes to L. This will imply what? There exists n2 belongs to the natural number such that x of 2n plus 1 minus L, this is less than 1. Oh sorry, for all n greater than n1, and this is for all n greater than n2, right? Then if we take n to be the maximum of this n1 and n2, then both will be satisfied. So then for all n greater than this capital N, x2n minus L is less than epsilon and x2n plus 1 minus L is less than epsilon for a given epsilon. This means what? This means the even term, and after this n, after the term xn, this all the terms, even terms and odd terms is going to be L, converge to L. So this means xn converges to L because even term and odd term are converging to L. So the limit has to be same, then it is convergent. And similar things for this. Now proof of 4. So we are given what? x2n, x3n and xn plus 1 are convergent, but we are not given that they are going to the same limit, right? So first we have to prove that they are going to the same limit. So x2n converges to, suppose, L1, x2n plus 1 converging to L2, and x3n converges to L3, suppose. We have to prove this L1, L2, L3 are same. So what we will do that? So we will take the subsequence x of 6n. So x6n is a subsequence of x2n and x3n also, right? So it is a subsequence of x2n and x3n, and x2n converges to L1. This means what? Every subsequence of x2n will converge to this L1, and since it is also a subsequence of x3n, so it will also converge to L3. So this will imply L1 equals to L3. Now if we take this x 2n into 2n plus 1, this subsequence, and similar thing happen, so this will imply L1 equals to L2. So L1 equals to L2 equals to L3, right? So all of them are L, suppose L, right? Now all of them going to the same limit, and we have proved that if x2n and x2n plus 1 goes to the same limit L, then xn is convergent. So this will imply, from the previous example, this implies xn is convergent, and all of them have the same limit, right? So 4 is proved. Okay, so let's take the next problem. Okay, so let yn be a sequence where y1 equals to 1 and yn plus 1 equals to 4yn plus 3 for n greater equals to 1. Okay, so we have to prove that, show that limit of this yn is 3, right? So this is the problem. So how will we prove that? We'll prove that this yn is a monotonically increasing sequence, and it is bounded so it will be convergent. We'll use this theorem that a monotonically increasing sequence which is bounded above is convergent. Okay, so we'll use this theorem. So to use this, we have to first prove this Yn's is a monotonically increasing sequence. Monotonically increasing sequence means what? Increasing means Yn plus 1 is greater or equals to Yn. We have to prove this. So we'll prove this by mathematical induction. So we see that y2 is what? y2 is 7 by 5, which is greater than 1, that is y1. So y1 is greater than less than y2. So this is the base case. So this is base. So suppose, so we are proving by mathematical induction. So suppose yk is less than yk plus 1 for some k, right? Then we have to prove this. To prove yk plus 1 is less than yk plus 2. We have to prove this. Then we'll say that this is monotonically increasing. So this is our assumption. Yk is less than yk plus 1, right? So this means 4yk plus 3 is also less than 4yk plus 1 plus 3, and if we multiply by 1 by 5, then it will imply this is yk plus 1, and this is what? This is yk plus 2. So this is proved. Okay, so this means Yn is monotonically increasing. So it is monotonically increasing. Now we have to prove it is bounded. So this means, so also we will prove this by induction. So Yn y2 is less than 3, right? Now suppose yk is less than 3 for some k. Now we have to prove that yk plus 1 is less than 3. To show yk plus 1 is also less than 3. Then we'll say that all the members less than 3. So yk plus 1 is what? Yk plus 1 is 1 by 5 times 4yk plus 3. Now yk is less than 3. This is our assumption. So this means this is less than 4 into 3 plus 3. This is 3. So yk plus 1 less than 3. This means Yn is bounded. So it is bounded and upper bound. This is bounded above and it is monotonically increasing. So this means Yn is convergent, right? So Yn is convergent. So it has unique limit. So suppose Yn converges to y, right? We have to find this y. We have to find this y is 3. We have to show that limit of Yn is 3. So we suppose Yn converges to 3, converges to y. Then we have what? Y. Now we have yk plus 1 equals to 1 by 5 times 4yk plus 3. Now if we take the limit in both sides, k tends to infinity. So this is going to be what? Y equals to 1 by 5 times 4y plus 3, right? So this will imply y is 3. 5y equals to 4y plus 3, so y is 3. So this is proved. Yn converges to 3. Okay, let's go to the next problem. Okay, number 5. So let xn be a sequence such that xn converges to x and all the xn's are greater than 0, right? Then we have to prove that root over xn converges to root x. That means the limit root over xn is root x. We have to prove. Okay. So let's look at the solution. So xn converges to x and all the xn is greater than 0. This means what? This means x is also greater or equals to 0, right? All the positive terms cannot converge to a negative term. Now first case 1 we'll do that. Case 1 is what? We are assuming x is 0. So xn converges to 0 means what? For a given epsilon greater than 0, we can find there exists some natural number n such that xn minus 0 is less than epsilon square for all n greater than n. I am writing epsilon square because next I will write root over xn. So this is less than epsilon square. Epsilon square is less than epsilon, so this is also going to be true since this is converges to 0. So this means what? This means mod xn is less than epsilon square. So since all the xn's are positive, so root over xn, this is positive term, so this is nothing but xn. So root over xn is also less than epsilon. So this means for a given epsilon, we have found that root over xn is less than epsilon for all n greater than capital N. This means what? This means root over xn converges to 0, right? So for x equals to 0, this problem is proved. Now case 2, we'll consider this x not equals to 0. So we are given xn converges to x. Now we are writing root over xn minus this. We have to show that this is going to be 0. So this is what? This is right. So this is xn minus x by right. So we can write this as this is less than root x xn minus x, right? Since this is positive, root over xn plus root x, so this is going to be less than 1 by root x mod xn minus x. Now this xn minus x is going to be 0 since xn converges to, so this is going to be 0 as n tends to infinity. So this root over xn minus root x also going to be 0 as n goes to infinity. So this means This means root xn converges to root x, right? So this is proved. Okay, so let's go to the next problem. If you have any doubts, you can ask me. Okay, so 7. So let un be a sequence u1 is root 2 and un is n plus 1 is root over 2 un for all n greater equals to 1, right? Then prove that limit un is 2, right? So you have to prove that un converges to 2. So u1 is what? u1 is root 2, means 2 to the power half, and then u2 is what? Root over 2 u1, which is nothing but root over 2 root 2, and this is what? This is half plus 1 by 4, or we can write this as root 2 1 by 2 plus 1 by 2 square, right? Now if you remember the geometric sum, we can write that is r plus r square plus r cube. This is okay, I'm writing this. This is x plus x square plus x to the power n is nothing but x into 1 minus x to the power n. Oh, sorry, I think this is 1 plus by 1 minus x, the geometric sum. So this is going to be 1 minus 1 by 2 square, right? Half into 1 minus 1 by 2 square by 1 minus half. So now let's u3 is what? u3 is 2 to the power half plus 1 by 2 square plus 1 by 2 cube, right? Then it is nothing but what? 1 minus 1 by 2 cube, like this. So un is what? un will be 2 power 1 minus 1 by 2 to the power n, right? Now you can clearly see, if we take the limit n goes to infinity un, then this is going to be 2, because since n tends to infinity, 1 by 2 to the power n is going to be 0. So limit un is 2. Oh my god, I have written this in red. So this one is proved, right? You understand it, right? Okay, let's go to the next problem. If xn is strictly greater than 0 for all n belongs to the natural number, and limit n tends to infinity x of n plus 1 by xn is x, then limit xn to the power 1 by n is going to be x. if the ratio is going to x, then xn to the power 1 by n is going to s, right? So you have to prove this, but first we need to prove two theorems of Cauchy. So Cauchy's first theorem, so it says if xn converges to L, then the sum, the sequence plus xn by n, this is suppose yn, then yn also converges to L. So this is the first theorem of Cauchy, and there are two theorems. First we will prove this. So proof, so xn converges to L, and we have to prove this in two cases. So case 1 is L is 0. Okay, if L is 0 for xn converges to L, this means for given epsilon greater than 0, there exists some m belongs to the natural number such that mod xn is less than epsilon by 2, right? Now for epsilon by 2 for all n greater than m, greater equals to m, right? Now also xn converges to L means what? Xn is bounded, so this means xn is bounded, so mod xn is less than some r for all n, right? Because xn is bounded, so we have mod xn less than r for all n and mod xn less than epsilon by 2 for all n greater equals to m. Now let's come to yn. So yn is what? Yn is mod x1 to xn by n. Now if we use the triangular inequality, we will see this by x1 plus, we are dividing it to m, and then from m plus 1 to n, since m is less than n, right? So this is n. Now using the triangular inequality, up to m we'll use this r, and after m we have this, for n greater equals to m we have this one mod xn less than epsilon by 2, right? So this is mod x1 plus mod xm by n and mod xn by n, right? So up to m this is less than r, so r by n, there are m terms, so this is going to be m r by n, m number of r by n, so this is m r by n, and after m this is less than epsilon by 2, so and there are number of terms is what? N minus m, so n minus m times epsilon by 2n, because all of the xi's are less than epsilon by 2 for n greater than m, so this is epsilon by 2n, n minus m times, right? Now if we sum it, we'll see that, okay, I think I have okay, now choose n1 belongs to n such that n1 greater than m and r by n1 is less than epsilon by 2m. If we choose such an n1, then we can see that mod yn is less equals to epsilon by, so r by n is less than what? Epsilon by 2m. So this is less than mr by 2n, epsilon, this is m epsilon by 2m, and this is n minus m epsilon by 2n. Oh, okay, mr, yes, this is epsilon by 2 and this is again epsilon by 2 for all n greater than this n1, because after n1 this is satisfied, r by n1 is less than epsilon by 2m, right? So this is going to be what? Epsilon. So what we have is that yn converges to 0, and yn is what? Yn is x1 to xn, so yn converges to 0. So for 0, if we take L to be 0, then we have proved that this x1 plus xn by n converges to 0. Now if we take xn converges to x, which is not 0, so we'll take another sequence, which is what? Xn minus x, then xn dash converges to 0. So if we use this case 1 to this xn dash, then we will see that what? We'll see that this yn, which is yn is what? Yn is x1 minus x plus x2 minus x plus xn minus x by n. This is going to be 0 by case 1. So, and this is nothing but yn is what? Yn is then means x1 to xn by n, and this is nx, so this minus x, so this going to 0. This means what? x1 to xn by n is converges to x, right? So we have proved this 0 for case 1 and not 0, then it is case 2. So Cauchy's first theorem is proved. Now we'll prove Cauchy's second theorem. So you understand the proof, right?
Yes, ma'am, the proof is clear.
Okay.
However, the only issue is that why did we choose in the case 1, why did we choose the value of n1, r by n1 in such a way relating it to
Because
epsilon?
we are getting mr in this line. See, in this line we are getting mr by n, right? So there is no epsilon, but we have to go to the epsilon at last. So we are choosing an n for which this happens, this r by n1, because epsilon is already given greater than 0. So we can find an n1 for which this r by n1 is less than epsilon by 2m, right? Because r we have find that what? It is bounded by r. So r is already fixed, epsilon is already fixed. So we can find n1 for which this epsilon less than epsilon by 2m. So we are needed to prove mod yn is less than epsilon. So that's why from r to epsilon we need this assumption, right? We have to
So
find
we are
n1.
actually, yes, ma'am. So we are going to such an n which is quite great that it will be satisfying with
yes.
these values.
we will find such, because this will be finite, so we can find some greater n1 for which this happens, because n1 is does not matter. For convergence we have to find a number, after that number all of them going to be less in the epsilon neighborhood of this yn, so we can choose any n which is greater. After that it has to be less than epsilon, right?
Understood, ma'am. Thank you.
Okay. So Cauchy's second theorem is if xn converges to L, then this x1, x2, xn to the power 1 by n converges to x. Okay, this is the Cauchy's second theorem, and we'll need this one to prove our main problem, which is question 8. Right, so first prove this. So we'll use Cauchy's first theorem to prove this theorem. So we'll take yn to be log xn. Right, now xn converges to x, so log xn will also converges to log x. See, this happens because this is continuous. You will see that in the next classes when continuity will come. If f is continuous, then xn converges to x implies f of xn converges to xn for all the sequence. So this is a if and only if condition. So that is going to use here. So log xn will converge to log x. Right, I am writing this. If f is continuous, this is if is continuous if and only if xn converges to x implies f of xn converges to fx. If this is true, then it is continuous, and if f is continuous, then this is also true. So this is if and only if condition. And log x is also continuous for x greater than 0. Since we are taking 1 by n, so all these xn's are greater than 0. Okay. Right. Okay, yes. So xn is greater than 0. So log xn converges to log x. Now by the first theorem of Cauchy, it says log x1 plus log x2 plus log xn by n also going to be log x, right? This is the nth sum x1 to xn by n. Since log xn converges to log x, this is also going to be log x. And what is this thing? So by the property of logarithm, this is going to be x1, x2, xn and minus 1 by n. This is goes to xn. And what is this? This is log of xn to the power 1 by n, which goes to log x. So again, this means if we take the e to the power x, this is also a continuous function, so this is going to be x. So this term also converges to x, right? So these are the two theorems of Cauchy. Now we'll prove question number 8. So question number 8 is what? Xn is greater than 0 for all n, and limit of xn plus 1 by x is x. Then we have to prove xn to the power 1 by n is x. Okay, so proof of question number 8. Right. So let's consider another sequence which is yn is, so what we are given, okay, I am writing this again. So xn greater than 0 for all n, and limit of n tends to infinity xn plus 1 by xn is x. And to prove, we have to prove limit xn to the power 1 by n is x, right? So we are taking another sequence where y1 equals to x1, and for n greater equals to 2, yn is xn by xn minus 1, right? So for n equals to 1, this is x1, and after that this is xn by xn minus 1. Now we are going to use Cauchy's second theorem on the sequence yn. So by the Cauchy's second theorem, what we have y1 y2 to yn to the power 1 by n converges to, see this okay, so yn converges to what? Yn converges to what? Yn goes to x, because yn is what? Yn is xn plus 1 by xn. After that is nothing but xn plus 1 by xn, and we are given what? Limit of xn plus 1 by xn is going to be x. So this is the same thing after first term. So this is x2 by x1, and this is we have taken n greater equals to 2. So y2 is what? x2 by x1. This is same thing. So yn converges to x. So by Cauchy's second theorem, this is going to be x. And what is this? This is y1 is what? y1 is x1, y2 is x2 by x1, y3 is x3 by x2, like this, and the last term is xn by xn minus 1. So to the power 1 by n goes to x, and it is what? It is xn to the power 1 by n goes to x, right? So limit of xn to the power 1 by n is x. So question A is this proved, right? Where? So this is done. Okay, let's so okay, for the last question, so the time is already 8:50. So last question, question 9. So this is a easy question, so you have to answer this. Is this sequence is Cauchy or not? Can you guess? Cauchy means what? Cauchy means for any, there exists n such that xn minus xm is less than epsilon for all, for a given epsilon greater than 0, there exists n for all n and m greater than n, right? This is the definition of Cauchy. This means what? Xn is Cauchy, right? So is this Cauchy? So if you can answer then I can end this. Okay, you can guess. Okay, if you are not answering, then so take epsilon to be, this is not going to be Cauchy. So there, so you have to find an epsilon. So what is the negation? So this is, if it is Cauchy, then this is true, right? What is the negation? Negation of Cauchy is what? This means this is for a given epsilon. So there exists an epsilon. So there exists an epsilon greater than 0. And this is what? For all nm greater than 0. And for each n belongs to n, there exists a capital N belongs to n such that capital N, capital M, suppose, then xn minus xm greater equals to epsilon for all n. Okay, I am writing, you can write this as n plus 1. This is same thing, is greater than, for all greater than n greater than n. So this is the negation. If it is not Cauchy, then it has to happen, right? We have to find a n. Okay, I think I am written this. This is not for all. There is no small n. So for n greater than n, right? Not for all. So for there exists some epsilon, and for each n we can find a bigger n than this n for which this is greater than epsilon. So this is the negation. So if it is not Cauchy, you have to prove this. So if we take x n to be an even number 2k, then x 2k is what? This is 1 plus 1 by 2k, and 2k plus 1 will be what? Minus 1 plus 1 by 2k plus 1, right? Now if we look at the difference, x2k plus 1, x2k. So this is going to be what? This is 2 plus, so this is 2 plus 1 by 2k into 2k plus 1, right? So this number is strictly greater than 2, right? So this means what? We have for a given n, for any n, for any or for each n in natural number, we can find a k which is 2n, for which this this happens, the difference is greater than 2. So it is not going to be close enough to 0. Xn minus xn is less than epsilon. So this is not going to happen, this. So the negation is true. So this will imply the sequence xn, the sequence is minus 1 to the power n plus 1 by 2n is not Cauchy, right? Okay, so this was the last problem. So if you have any doubts, you can ask me about this today's session. Okay, so you don't have any doubts, right? Sukriti?
Yes, ma'am, clear till yet.
Okay, okay, then we'll meet in the next week, right? So let's end this session. You can leave now.
Thank you, ma'am.
Okay, thank you.